right, so this is actually block 3, and they have kindly allowed me a little space and time to work on this problem number 6 that I want to get done for you guys. So we got this trajectory representation, projectile trajectory, can't even talk today. And it gets fired off a cliff like this, and of course we have a y naught of 30, and y final is going to be 0, and of course we have an x initial of 0, and we don't know what x final is, so the first thing is we want to calculate the time from launch until the projectile hits the ground. So here's the thing. The time that the projectile takes to hit the ground, this time only depends on the time to fall. And we know this because we actually did that. We actually tried to do that. We did that analysis of the video a few weeks back where we had one projectile drop and the other go like this. And so we know that those times were absolutely the same for each object. So now what we can do is we can look at our formulas in the y direction. So I can say y equals -1/2 gt squared plus v naught in the y direction times t plus y naught. That's our first equation. Now here's the deal. I'm firing this thing horizontally at 35 meters per second. So that makes this v naught x. What that means then is that v naught y is going to be 0 meters per second. So that actually lets us put 0 here. I've already got my picture labeled, so I know then that 0 is going to be -1/2 times 9.8 times t squared, which is what we're actually trying to figure out, plus 30. So then I'm going to actually end up getting, when I do my algebra, t squared ends up being 30 divided by 4.9, and then t is going to end up being the square root of 30 over 4.9. So I'm going to actually put that in my computer right here, get the answer. And that ends up being 2.47 seconds. It's awesome. Now, the horizontal distance that the projectile travels before it hits the ground, that's going to be x equals v naught x times t plus x naught. Okay, because we're talking about a horizontal distance. So what I'm going to do is I'm going to go ahead and get that answer now by just plugging in. So x equals 35, that was the number from up here, times t, which is 2.47 seconds, plus 0. And so when I go ahead and solve that, that's going to be 35 times 2.47, and that ends up giving me 86.45 meters from the base like that. Now, we want to calculate the speed at point A and point C, where A is the maximum height and C is the speed just before impact. So at A, our maximum height is when we first launch. So when we first launch, we got v naught x, and that's just 35 meters per second. Now, for C, the speed just before impact, well, we need v naught x, we need vx final and vy final, because when we say the final speed, that's again the magnitude of the velocity vector, which is vx squared plus vy squared. Now the first thing is vx is just going to be 35 meters per second. And vy, well, that's the speed at the bottom. So let's go ahead and get that using our formula. And that formula is going to actually end up being vy squared equals 0 squared plus 2 times negative, well, actually it's 2 times, negative 9.8 times 0 minus 30. So vy at the bottom, when I simplify this, is going to actually work out to be, just get it, just putting it in my computer to get the answer. That ends up being 24.25 meters per second. So when I want to get my speed, that ends up being the square root of v naught x squared plus vy squared. Again, it's because v naught x and vx are the same because it never changes for x because it doesn't accelerate. So we're going to end up getting 35 squared plus 24.25 squared, all under a square root. So the final speed, when I do that math, when I actually do that, ends up being, if I do this right, 42.58 meters per second. So that's pretty much the solution to that problem. That's kind of our first packet done. And then in the next videos, I'm going to move on and do the rest of the packet, like the second packet that I do with the review stuff.